As you saw, I'm going to be talking about 3D flow imaging. The outline of the talk is as follows. I'm going to first talk about volume flow. The major portion of this talk is going to be about volume flow. To me, this is one of the best applications for 3D imaging, and I think its time has come, and we should be doing this in the very near future. Then I'm going to be talking about true flow, true real 3D flow, and that is mostly an intro to pressure gradients, measurements. So first, I'm going to be talking about volume flow. The volume flow technique I'm going to be talking about was initially described by Hottinger and Meindel in 1974. However, really, it was described by Gauss at the end of the 18th and 19th centuries when he lived. The technique is based on what's called Gauss's theorem, which says that volume flow is a flux across any surface. And I'm going to be describing what that means in just a minute. The technique really was not viable until 3D and 4D imaging became available, and now since both of them are available, the method could be employed to actually measure volume flow, volume blood flow. Okay, well, I'm sure you're all aware how blood flow is measured now. There are many limitations to the actual acquisition because of the way that we acquire the data ourselves using ultrasound. The properties that we would like to have, which are not available now, are we would like the volume flow technique to be angle independent. We'd like it not to assume any vessel geometry. We'd like to not have to assume any flow profile, and we'd like the measurement to be time independent. None of those things exist presently. This is a common carotid artery, and this is an example of how volume flow might be detected presently. First, there's a Doppler sample line, which you are all used to seeing. The sample volume spans the vessel. This first has to be angle corrected in order to compensate for the change in the flow measurement based on the Doppler shift. Then you have to estimate the diameter. That estimation assumes that the cross-section is a circle. The other thing is that the measurement is one-dimensional. As you can see, we are sampling along a line. That implies that the flow profile is cylindrically symmetric. And since the diameter that we're measuring is fixed, this doesn't compensate for any of the pulsatility in the blood vessel. All of these things are approximations which are almost invariably wrong, and because of that, very few people use volume flow as a standard portion of their imaging modality. Once you actually make this measurement, once you actually set this all up, then you basically look for the mean velocity. You'll notice that the envelope is what is being measured here. You measure the mean velocity, multiply that mean velocity times the cross-sectional area, which you assume is a circle, which we've already said is an assumption that may not be correct, and that's the volume, that's volume flow. However, volume flow is really can be broken down into described in another way, which is much more robust. It turns out that if you have a whole bunch of velocity vectors that are perpendicular to a cross-sectional area or a slice, if you can get every small unit of area, which is what dA sub I means, and you can get the flow, the velocity perpendicular to that slice, the mean velocity, all that product, and multiply it times the area, that product is called flux. If you then sum all of these fluxes up, and actually it's integrate if it's a continuous process, then that sum is volume flow, and that's all this says. This is the velocity perpendicular to this area. If you have a discrete sampling, which is what we have now, then you take every local velocity, multiply it times a small unit of area, and that's volume flow if you add them all up. What's interesting about this is the velocity, because it's Doppler, is multiplied times the cosine of theta, which is the Doppler angle. The area, however, increases by the cosine of theta. For instance, if you have a circle and then you rotate it at an angle, you get an ellipse. The area of that ellipse increases by the angle that you rotate it relative to the normal, which is the Doppler angle, which would be equivalent to the Doppler angle. And so that's divided by the cosine of theta. If you can't, these two products cancel, and then all you end up with, again, is local velocity times area. And this now is angle independent because the cosines cancel. I'll make that more clear in a few minutes. So if you do all that stuff, you have volume flow. Okay, so what do you have to do to get this? Well, if this tube, or representation of a tube, is a blood vessel, the green arrow is the direction of the flow. This plane, this black plane, is what a cross-sectional ultrasound slice would look like in one dimension. So we'd have a transducer up here producing this plane. Actually, the plane is two dimensions, but we're cutting across this vessel. Then the intersection of that plane with this tube, or the blood vessel, is this yellow circle right here. If you have a very small unit of area in that cross-section, when the blood flows through, it displaces that area in a unit of time to produce this local volume. That local volume divided by the time in which it was displaced is the local flux at that position. If you take all of these guys, all of these small areas, and add them up, that, like I said, is volume flow. The problem is that we sample across this plane. This S represents a single cycle sine wave, shows where the ultrasound is going in this particular rendition. It turns out then that the Doppler that you detect are Doppler shifts in this plane. That means that the flow that we see is totally orthogonal or perpendicular to the flow we want to detect. Therefore, every bit of flow that's detected in this plane using a standard ultrasound, if you cut across the plane this way, cut across the vessel this way, would not be contributing anything to volume flow. Because of that, we have to do what we do now. We have to do sagittal imaging and estimate the cross section with a circle and make all these symmetry assumptions. However, if we have a 2D array or can sample in, which would allow us to sample in 3D, then what you could do is propagate the sound perpendicular to this surface. So the sound beam now is going right at that displaced volume. That means that the normal, or the perpendicular flow to this plane is now exactly what you measure with with standard Doppler at that position. Remember, this flow is now perpendicular, is now in the exact line of one of these rays from the ultrasound scan head, and that means that the Doppler shift you measure is actually perfectly corresponds to the velocity of the blood at that point, which, remember, is exactly what we want. So now all we have to have is that area. We now have the velocity independent of angle at that point, and that's volume flow. So instead of having to correct all this stuff that we had to do in 1D with a 1D array, we now, using a 2D array, producing a 3D image, overcomes the major problems that I talked about. To show that it's angle independent, we're now going to rotate the scan head, and you can watch the cross-sectional area get larger as we rotate the scan head. To make this more clear, if you use the normal component, that would be the component of the blood that's going perpendicular to this plane, which would be now right at the transducer. You notice as you rotate the plane, this component gets shorter. But this area gets larger in exactly the same proportion. And since it's the product of that component times the area, it's angle independent. So volume flow is angle independent, which is a huge plus. And this is just to show it again. This is the cross-sectional area. You're sampling the blood flow in this direction, perpendicular to that area. That's the Doppler angle, which you can see here. The angle to the blood flow, there's the blood flow there. The angle's there. The velocity that you measure, the correct velocity is that what you measure times the cosine of theta, but the area is divided by the cosine of theta, and they cancel. So volume flow is angle independent. Okay, so we've tested this technique in flow tubes using blood mimicking fluid. We've tested it in dog carotid arteries and femoral arteries. We used a GE Logic 9 clinical 3D scanner. This is a standard scanner. We used linear array probes. We also used a curved linear probe. And these are the linear arrays. And then we had a research interface where we actually took the Doppler data and did this sum to calculate the flux. However, like I said, this is conceptually quite simple and could easily be done on the machine. The integration calculates the flux, as I said, and that gives you volume flow. There's some partial volume issues which I'm not going to get into, and we use power Doppler to correct those.